Hello, I'm Mike McCulloch. Today I thought I'd explain relativity in a very simple manner. So, around about 1900, the speed of light had been measured in various parts of the world, and it was always found that it was the same, no matter where you measured it, California or Germany, which was very odd because the Earth is a rotating sphere, and so the motion of the Earth was different every time they measured it. So they kind of expected that the speed of light would be different, but it wasn't. It was always the same. So people were puzzling over why it was that the speed of light was always the same. I mean, if you're on a train moving forward and you throw a ball in ahead of the train, then the ball has the speed of the train plus the speed you throw the ball at. But light didn't seem to work that way, which is very puzzling to classical physics. And it was Einstein, a few other people, Lorentz and Poincaré as well, but mostly Einstein, who understood deeply what was happening and attributed this to time and space, our definitions of time and space. And there's a very nice illustration which uses two mirrors with a beam of light bouncing between them. So this would be a kind of a clock. Two mirrors, a beam of light bouncing between them. Each bounce of the light represents an interval of time. So it's shown here. The light just goes in a straight line between the two mirrors. But if the mirrors happen to be moving relative to you, then it's rather different, because the light has further to go. From your point of view, it has to go along a diagonal line. So it has to travel further. So somebody without knowledge of this empirical speed of light might say, okay, but the light travels with the mirrors, sideways with the mirrors, so there's no problem, the time doesn't change. But Einstein knew that they'd measured light, different parts of the Earth, as I said, and it made no difference to its speed. So he said, okay, well, the light has to go at a constant speed, so it takes longer because it has to now go along a diagonal path. So this is interesting because it implies that the time measured by the clock has slowed down, because the light is taking longer to travel between the mirrors, and so each time interval is now longer. But Einstein said, well, that doesn't matter, that's okay, because we can never directly see time anyway. That's a kind of abstract concept. So let's allow that to vary, whereas the speed of light that we can actually see, we can assume that's constant. We can say that's constant. So this was the step that Einstein took. He said that we should, it's a philosophical approach in that we should trust whatever is directly observed, and we can mess around with what we can't see anyway to make it fit. So you could argue for and against that approach, I suppose, but that proved to be very fruitful. Although, of course, it is very abstract, and in a further video I'm going to show how I can actually derive the same thing in a less abstract manner. So, and it turns out that mathematically you can work out the equations of special relativity very simply from this mirror experiment. Okay, well, I hope you've enjoyed this short, and I look forward to seeing you next time, tomorrow. Goodbye.